Let's review a little bit where we got so far. I just want to recap a little bit. We've got the integral. We've focused a lot on integrating, not so much on differentiating forms. And I'm going to switch to differentiating in a second. But the integral of a one form, let's see, so integrals, we got one form on a curve. We had the integral over the curve of some one form alpha is just the integral over the domain of how it's parameterized a to b of, we call the parameterization r, we said r star alpha. And sometimes actually we often just drop the parentheses, r star alpha. But it really is this thing, this operation r star acting on alpha. Okay? And then a two form on a surface, it's exactly the same. That's one of the big benefits of forms, is it uniformizes everything across every possible dimension. The mechanics, the actual calculation you end up getting is of course different, but the idea, the definition, the basic definition is exactly the same. To integrate over a surface in R3, we pulled it back to a domain, and here we happen to call the parameter map phi, but that's not really any different, okay? And then it was working out the details of this and how it worked out with wedge products and D's and things that turned it into something different, produced something equivalent to like a cross product kind of calculation here, a flux. Okay, so secretly, even though that's really just the definition, working it out involves knowing about D and the wedge product. Well, that's what I really want to talk about. Well, the one thing that I want to remind you is that if you have a map, let's say take the phi example, the naturality of D means that you can just, if you pull back the D, or it's the same as if you pull back the function, then you do D. And the same was true, I claim, for the wedge product. Which you could believe if you think about this pictorial version of the wedge product. We just drew the one form stack picture for each and just drew them together. And then if you pull that whole picture and kind of translate that to another universe, it should be the same thing as if you draw them separately, translate them first, and then just say, oh, there, I've drawn them together. So in the picture, it's really fairly natural to believe that. Okay. And then, of course, so far we've only been taking D of a function, and I want to get us ready to talk about D of like a one form. The cool thing about D is it's much more than the gradient, much more. As soon as we start letting it act on one forms, not just zero forms, which are fancy name for functions, or on two forms, three forms, four forms, five forms, depending on how far we go, we're going to get something cool. Okay, so that's what we've seen so far. Oh yeah, and then of course the wedge product. Remember that we have that like dx wedge dy is minus dy wedge dx. It's associative, but it's anti-commutative. And in fact, it's not too hard to show that in general, alpha wedge beta is minus beta wedge alpha if alpha and beta are one forms. But in fact, the more general thing is that alpha wedge beta, it's minus 1 to the, and I'm going to use a little weird notation, I'm going to use an absolute value of alpha times absolute value of beta. And absolute value doesn't literally mean absolute value here. It means the degree. What kind of form is it? So if alpha or beta were a zero form, this would be plus. Well, that's a function. That's saying that if you just multiply a zero form in, it doesn't matter if you do it on the right or left. That's good. If they're both one forms, you get a minus sign. If one of them is a two form, then in fact it still commutes. So if either beta or alpha is an even form, it turns out it really still commutes. That really isn't a new fact. It turns out to just, if you just break alpha and beta up into their component one forms, it really is provable from that. But that's a nice thing to know about the general version of anti-commutativity. It's not always a minus sign, definitely. Okay. So speaking of anti-commutativity, here's a question. I keep alluding to like things like four forms. What about four forms, but specifically on R3? Well, how would I build such a thing? I would take dx, wedge dy, wedge dz, wedge, whoops, wait a minute, there's nothing left. Well, okay, let's just reuse one, wedge dx. Uh-oh, The problem is that that's equal to, I can swap these guys, then swap it here, then swap it here. It's plus or minus, I don't care. Dx wedge dx, wedge dy, wedge dz, but that's 0. So this is going to happen whenever I repeat. So if I try to build a 4 form or a 5 form or a 6 form, I'm always going to get 0. So there's no such thing. Now, this was relying on the fact that I only had 3 different variables. If I have 4 variables like w, x, y, z in R4, then I can totally do this. I could have dw, and it's fine. So you're only ever going to get up to n forms on Rn. So on Rn, we get up to n forms, and those are totally useful and meaningful and very cool. Okay. So in R17, you're going to have everything from 0 forms up to 17 forms. So that's an important thing to note, that even though we've got these various different species on a particular space, they stop after a while. Okay, so now here's more about D. Okay, and in particular, we want to figure out what would like D of a 1 form be. Well, there's different approaches to this, and my ideal approach is probably different from what I'm doing right now, but I'm going to be pretty direct and somewhat calculational. You're going to have to take a little bit on faith. For example, the idea that D of a 1 form should be a 2 form. Hopefully that's not shocking, because D of a function was a 1 form. So D of a 0 form was a 1 form, D of a 1 form is a 2 form, and in fact, D of a p form, in general, is a p plus 1 form. Okay. And this is really key to the theory. The D is going to, in one fell swoop, encapsulate all the derivatives we've ever seen, div, grad, and curl. The way it does that is it works on different kinds of forms and spits out different kinds of forms. It's not all just a vector field to a vector field or a function to a function. And the way it systematizes things is it goes, the D of a p form is a p plus 1 form. There's some very deep reasons why it has to do that, which I'll get to later, but I'm gonna save the deep reasons. I'm not gonna start with them, even though I'd kind of like to. Okay, it might be just kind of too abstract if I did that. Okay, so here's our first example. D of dx. That's the simplest 1 form I can think of. And let's just draw that in 2 dimensions. It's exactly the same in 3 dimensions or higher. There's the picture of dx, uniformly spaced, sort of uniform, along the x-axis. These the stacks. And the only thing we need to know right now is the idea that D should have something to do with change. It's a derivative after all, so it has something to do with how is dx changing. Somehow it's supposed to be encoded in a 2 form, we'll get to that. But you know what? dx is constant. No matter where I plunk the pen down, the marker down, I see the same thing. So this really should be 0, because the derivative of any constant kind of object be 0. Okay, so that's something we need to know. All right, now what about D of f dx? Something where it isn't constant. Maybe they're really closely spaced here and then not over here, or maybe they're really far here and really closely spaced here, so that f varies as a function of y, so it's more interesting. Okay, so that, for example, this guy doesn't look like they match up. Well, all we have to believe now, I want you to take on faith, is that the basic principle of derivative of constant, even if it's kind of this weird 1 form constant, times a function, the constant should pull out. And so I'm going to get df, and then I need to multiply df and dx. Well, the only legal way to do that is a wedge product. One really important thing here is that I did not write it as dx wedge df. Order matters. As soon as I get to wedge product of 1 forms, it totally matters what order I do it in. And I had them as f on the left, dx on the right. I'm not going to change that. Okay, so that's something that's hopefully plausible. It's just sort of the principle of constants coming out. It's just coming out on the right here. And what about d of f dx plus g dy? Well, let's hope that this thing makes sense for this thing to be linear, and indeed it does. Plus dg wedge dy. Alrighty, that's pretty cool. That's actually a nice rule. And let's see, what is that going to actually mean? df, remember, dx and dy, we're really content to leave those just sitting there. Leave them alone is what I'm trying to say. Leave them sitting there, because those are d of our basic variables, and we like to express things in terms of something times dx and dy. But df usually would be a more interesting function, so would dg. So this is actually going to become something pretty interesting. It's going to be d partial f partial x dx plus partial f partial y dy all times dx plus partial g partial x dx plus partial g partial y dy. Hey, wait a minute. dx, oh, then these are wedge products here. Hey, df wedge dx is 0. dy, oh, there's a dy here. dy wedge dy is 0. Oh, how does this simplify? That's very intriguing. Okay, so that's going to be, this is the only one that is left here. That's partial f partial y dy wedge dx. And then this one is the only one that's living here, plus partial g partial x dx wedge dy. Hey, you know what? These guys are negatives of each other, so it's negative df dy plus dg dx dx dy. And we've got it in terms of just one function times dx wedge dy. For example, in R2, that's the kind of thing we could integrate. We just integrate that directly by just erasing the wedge product. This should look very familiar. This is the scalar curl. Not everybody uses that terminology, but it's the Integrand and Green's theorem. Okay, and it's just basically one component of the curl. It's as complicated as the curl gets in R2. And so we've got here, hey, this, you could think of this as kind of a replacement for fi plus gj, a vector field, and the d has automatically, without having to be told to, has automatically created the scalar curl. And guess what? If this was plus hk in R3, I bet you can guess what's going to happen if we expand this out and we look at all the minus signs, blah, blah, blah. It's going to be exactly the regular three-dimensional curl. Okay, so that's going to be, we'll do that explicitly probably in a little bit, but I don't want to do a really complicated calculation yet. Okay, so that's super cool, and a super curl. What about, let's press on a little bit though. D of f dx wedge dy. Suppose you have a 2 form. Well, if f is just 1 or a constant, then this should be 0. Okay, and so that's one special case. But let's see, what should it be even if f isn't constant? Well, if we again accept this principle that this is basically a constant object, even though it's a funky kind of constant object, it should pull out, and I should just take the derivative of f. Okay, that's cool. So that really basically tells us how to take the derivative of anything explicitly. You just put d on that function, and then you just leave the rest alone. And then, of course, I could have this plus g dy wedge dz, etc. And we'll do that example pretty soon. But that's basically enough to really define it. However, it's not the most elegant way to define it. Mathematicians wouldn't really like that way of defining it or talking about it because it depends so much on using coordinates. And that's the quick and dirty way to do things, definitely, but it's not the most elegant way. I want to do a few more coordinate calculations real quick to show you some properties here. What about, we know that I claim that d of dx, because dx is essentially constant, should be 0. But there's a really, really fundamental principle here. And that's that, okay, dx looked like this. It was constant, okay. But df is going to look something different. We know that the sheets still kind of fit together, but they could be curvy. And they could even have a kind of a... Now that doesn't look constant at all, and it might be a little surprising to learn that this is actually still going to be 0. But here's one reason why. There's actually many, many reasons why this should be 0. And we'll talk about some of the other ones later. But one of the simplest ones is the idea of change of variables. Remember that I could have a change of variables that actually made these pictures equivalent. There's lots of coordinate systems, for example, where the coordinate lines, they're not lines at all. They're not straight. They're curves, like polar coordinates or something. These could be related by some transformation t. And I know that t is supposed to respect this derivative, the d. And so if d of dx is supposed to be 0, d is supposed to give the same answer here. That it treats this just as simply as dx does. That's a weird thing, but it's an absolutely fundamental thing. turns out then that d of df is always 0. Okay, and that's the first explanation I'm going to give for a very, very profound thing. And in fact, it turns out that d of d alpha is 0 for any p-form alpha. Or to summarize, d squared equals 0. And that's going to be, that's the neatest, coolest property of D, and it has wonderful geometric and topological significance. It's a hugely important thing. But it's a little bit one of the more mysterious ones, one of the most unexpected when you first see it. You might want to think, though, if you know your vector calculus, you might want to think about, are there combinations of derivatives we've seen that automatically give 0? Are there other operations, like sort of geometric topological operations we've ever seen, where if you do it twice, you automatically get 0? Well, there's none of those are coincidences. It's all part of the same fact. Okay, so